Welcome to the 6th Annual Soilcraft Conference. Join us as we listen to world-class speakers in the space of regenerative agriculture, as well as human health. We grow food. Food should nourish us, and often we find that our modern food is laden with unwanted synthetics or void of the minerals and vitamins we need to thrive. We endeavor to host this conference for your inspiration and education. Our calling is to help you produce food that heals people and our planet. Join us in this journey to become better stewards of our bodies and the world we abide in.
There we go. Here's a little bit more electrical conductivity, just to give you an idea of how much energy is in the soil when you're dealing with a microbe. Did you know, and maybe you don't, that most cells easily contain 0.5 volts? And that came from E. coli, which is a really tiny bacteria. A larger cell will contain even more than half a volt. That is a massive amount of electricity. Let's just say you have 100,000 microbes. That is 50,000 volts. Just 100,000 microbes. What if you have 2 million microbes? That's 1 million volts. You need that energy. That's what your crops are surviving on. Not only do you need that energy, but you need that energy to get into the plant. And that's partly what this is all about. Electrical conductivity. You need to have that energy, and that energy needs to flow in a controlled fashion into the plant. So how can you have that much energy? You might be thinking to yourself, well, if I'm walking on my field, which you're hoping is a little bit bouncy, then why is it not exploding underneath my feet and catapulting me 20 feet into the air? The reason why is because that energy is in a controlled environment called a cell. It's contained, kind of like a battery. You can step on a battery and you're not going to usually get electrocuted from that. It's the same thing with these microbes. It's contained, it's under control. That's why you're not exploding and going 20 feet into the air. But do not doubt me when I tell you that there is a massive amount of electricity in the soil if you have high microbial life. So high microbial life is really good. I think that's one of the take-home messages that you're getting right now. So much so that back in 1974, yeah, this has been known for a long time too, you could have just a 0.5% solution of glucose, sugar, which can increase the electrical conductivity levels in a soil which is relatively dead. And that this will reach maximal conductivity, which is optimal, in aerobic conditions. The aerobic conditions is oxygen. And when you have a lot of oxygen, you have a lot of aerobic microbes. These are the ones that you want in the soil. You want about an 80-20 ratio, about 80% aerobic microbes, 20% anaerobic, because the anaerobic ones have a role to play. You just want to make sure that it remains as a minor role. You don't want them to take over and become 80-20 in reverse. But the aerobic ones need to be there. And those ones need sugar. They need sugar. This is the main energy source for life on this planet. Like it or not. Despite what you have heard, our bodies need sugar. If we deprive the body of sugar, we will make sugar from fats and proteins. It's not the ideal way to go, but that's how desperate the body is in order to get sugar. And the microbes need it too. Okay? So I'll be talking more about that tomorrow. So it's now time to begin the chart. I've showed you the chart before for bricks. I'm now going to make a chart for you for electrical conductivity. So no need to take pictures right now. I'm going to start filling it in right now. Okay? All right, let's begin. The region over here between 0 and 200. And I hope you understand this can also be like 0 to 0.2, depending upon the scale. I'm just going to use the 200 scale. From 0 to 200, plants aren't doing well. Stunted growth. you don't have enough electrical flow. And so because of that, you will notice it, and your plants will suffer from it if you are between 0 and 200. We are often below 0 to 200 in Florida. However, once we get near some of the roots, we realize, it's actually doing a little bit better than we thought. But this actually prevents a lot of plants from growing in Florida because of our sandy soil. So that's what happens when it's too low. Next, we get a comfortable zone between 200 to 1200. That's the comfortable level that most plants are usually doing okay at. Okay. This is where vegetative growth is optimal. It's on the left side, between, let's say, 200 to 500. Certainly 600 would be fine. At this point, your plants are putting on leaves, stems, roots, and this is what they need. They don't need as much energy, but they need some in order to get things moving and in order to make that plant grow. At that point, once it gets to the point where the plant is happy and it starts to move into the reproductive phase where it's producing seeds, fruit, flowers, this is when things really pick up. You need a lot more energy in order to make the sepal, the petal, the stamen, the pistil, to put all of the nutrients inside a seed that are necessary in order to make the complexity of a fruit, such as an apple or an orange. Things get very difficult at that point. You need a jump. And that jump in electricity means that reproductive growth is optimal at the high end. So therefore, if you're looking at 800, most plants are going to be very comfortable with 800. 900 is certainly not bad. But you can see it can get to be a little bit problematic if we keep going up, which of course is exactly what we're going to do. Now in this vegetative growth and then reproductive growth, two different stages, this is what I call organic conductivity. Why do I say that? Because the literature tells me that they cannot get the conductivity of any soil in a laboratory above 1200 without putting on artificial salt. So they did their best in order to throw as many organic stuff at it, organic salts too, and it peaked at 1200, stopped. Therefore, if I'm going to get a reading at 1300 on your field, I know that you have some artificial salts on it because I know you can't get that high. That's what it's telling me. Even more so for at 1400, 1500 or above. So this is organic conductivity. Wow. There we go. This is the uncomfortable zone. When we get above 1200, plants are universally uncomfortable. I got finished telling you that some are better able to handle this, some are not, some will be dead depending upon how high we go. Others will be struggling. And then, of course, some of the weeds that I just mentioned too will be at the tail end of this, doing their best in order to regenerate the soil, because that's their job, in order to put as much sugar into the soil, get the microbes into the soil, and start stabilizing the salts and the electrical conductivity, assuming, of course, that you're not putting more salts on in order to compensate for that. This is inorganic conductivity. It is an uncomfortable stage, and it has been reached by a lot of plants. And then we finally get to the dead zone. Some of you in this audience right now, I am quite certain, have dead zones on your property. Those are the zones where you can't grow anything. Not even weeds will grow. It's usually at the low point, especially if water's flowing and you're putting in a lot of salts. They will collect in certain pools. And at that point, the conductivity will be so high that you won't be able to grow anything. Nothing. That's a dead zone. These dead zones are common on a lot of fields due to the overuse of salts. This is one of them. So while I was in Mexico, I was passing by the salt flats. So I took a picture of it right now. No plants. Conductivity, so what are you thinking right now? You're thinking like, what is this, 2,500? 3,000? 4,000? Try 20,000. Nothing will grow here. And then, every once in a while, I would pass by I can't really see him here, but every once in a while I would see a plant, and it would be growing in the middle of the salt field. And so I was with my host, and I said, whoa, look at that. Do you see that plant? I was excited, like, whoa, do you see that right there? There's a plant growing in the middle of that right now. That is so cool. And of course, he's so casual about it. He's like, Tom, no. He goes, let me tell you what happened. An animal was passing through across the salt flats, stopped, let it rip, and then moved on. And plants will actually grow out of those patties. I can't call them cow patties because any animal that passes by has the potential to help. And so when you're dropping poop along this, we actually do get plants. And I ran across several because this went on for miles and miles and miles, but we'd see little patches of just a little bit of vegetation coming up, and that patch was obviously a low enough conductivity in order to handle some particular types of plants. But this is about as dead as you can get right there. So, all righty, you might want to go ahead and take a picture of this one. This gives you an idea.
Dr. Tom,
Whoop.
I have a little present back here for you.
You have a present? Where am I looking?
Right back here. Back here. So we got 10 minutes, but I opened up your can. This is your reward for only going 10 more minutes.
Can I stop
right
the
here.
presentation now?
No. No, you got 10 more minutes. So
Yeah, otherwise, if I don't finish this in 10 minutes, I'm not going to get my
condensation
Mountain
over
Dew.
here, so just a little bit of
I
dingling
want
over
that
here.
Mountain Dew
All right,
so
10
bad.
minutes.
It's not going to work on me, Joe. Still got a little bit left there. All right, thanks for the 10-minute warning. In such a brazen way, too. I appreciate that as well. All right, I already talked about foxtail and kochia. Those are the weeds that can handle the highest soil conductivity. Usually when you get a little bit beyond that, you're now in the dead zone range. But you will see that there are many crop plants that are listed here. Green beans, they're terrible. They're awful. So if you have highly conductive soil, they are starting to suffer bad at 900 to 1,000, which is almost pathetic. But green beans just have a terrible, terrible, terrible way of not handling electrical conductivity, therefore at the bottom. Lettuce and cowpea are pretty low too. Then we got clover, grapes, and peppers. By the time we get to the top right there, bingo, we got the barley. So I've talked to many farmers before, and they say, I got highly conductive soil. And I was like, what am I going to do? My crops are not looking well right now. And I said, have you tried barley? Well, why would I try barley? I was like, because right now, that's probably one of the few things that's going to grow that will give you money, that you can actually make money on. Do you want to support your family? If you do, you might want to switch to barley, and then after a year of this, maybe 2, you can start moving down the chart right now, because each one of these has a differential ability in order to handle electrical conductivity. Yes? I don't know. That's why it's not there. Oh, I had it on another slide? Well, in that case, you caught me off guard, so kudos to you. Huh?
It was foxtail millet.
Oh, foxtail millet. Well, yeah, the foxtail is obviously much, much higher, so I would assume that pure millet would be in a similar, but I don't know for sure. I know some of you think I know everything, and in many cases you'd probably be right, but in an attempt to be humble, I will tell you that I do not know everything, and I'm hoping that this, fake humility right now is permeating your mind right now. So if all of you got a picture of this right now, let me continue on. Lettuce. I just told you it's not very tolerant. So I got this picture of lettuce someone sent to me, said, is this a tip burn you were talking about? I said, absolutely it is. You will notice that the tip burn is occurring at the tips. Sometimes it doesn't quite cover the entire edge of the leaf. It's usually concentrated towards the tips, and the conductivity, the worse it gets, the more it burns back when that happens. Wow, we've got this beautiful. And now, part of the solution, I need to teach you a little bit, in the few minutes that I have left, about calcium deposits in pipes. So if you have high calcium in your water, high TDS, hard water, it lines your pipes, it gets ugly. This is the type of thing that you do. How do you get rid of it? You get rid of it with a water softener system. The water softener systems are very good at cleaning out your hard water. But what do they use? Salt. That is correct. Some of them use sodium, some of them use potassium. Most people choose sodium because it's cheaper. Many agriculturalists, if they have a water softener system for agriculture, will usually choose potassium because potassium is obviously more amenable to a plant, but you do pay a little bit more when you do that. So the salts are used to compensate for calcium.
Did you know your irrigation water might be your greatest untapped opportunity for improving soil health, especially when it comes to electrical conductivity? In many cases, irrigation water actually create conductivity issues. Elevated levels of ions like sodium and chloride and compounds like bicarbonates can disrupt soil structure, limit nutrient uptake, and harm your microbial life. But with the Rainbox AOP, we transform water from a potential liability into a powerful tool for regeneration. By increasing dissolved oxygen, the Rainbox system promotes stronger roots, amplifies beneficial microbial growth, and supports aerobic soil conditions. It also reduces water viscosity and eliminates biofilms from your pipelines, letting your pumps run smoother while improving infiltration, reducing compaction, and enhancing the soil's natural conductivity balance. Your crop's number one input is water. Make it count. Rainbox turns every drop into a biologically active, soil-building solution. Contact us so that you can learn how easy it is to augment your current irrigation system and empower your water to do more.
And that works in reverse too. How can you quickly take care of salts? And the solution is going to be calcium. So here we've got, did I just go forward? I do not know what this is doing. All right, here's a plant where we've got the tip burn that extended around the entire leaf. Quick corrective measures occur, and when you do so, all right, I'm going to do this. Wow. There we go. And if you quickly correct it, a new leaf that comes up is no longer displaying the electrical conductivity problem, so I can take care of this with calcium. Now, of course, the tip burn remains, and so you pretty much have to wait until the next year. Once the next year begins to see if you had an effect upon the electrical conductivity of the soil, this is the same plant. It's not a different plant. Same plant comes up, it's got beautiful leaves, and we no longer have tip burn. It's relatively easy to take care of it if you know what you're doing, so I'm just giving you some ideas about how to correct some of this if you need to change things quickly, such as within a season. So this just kind of gives you an idea of what happens inside a plant. The plants also know this too. Calcium takes care of salt, salt takes care of calcium. They can take care of one another, and the plants know this. So in the plants, this is plant sap data. We got 1,900 data points in this graph. We can see that the salt levels, which are here in blue, are increasing very, very slowly, and then they start to jump up. At this point, the calcium is also remaining relatively steady at this region. Once the salt starts to go up, we see a jump. Here's the calcium jumping up. 1, 2, 3 data points, much higher. Before we were at 2,000 ppm for calcium. Then we jumped up above 2,000 for 1, 2, and 3. Salt continued to decline, and then what happens? The plant just releases massive amounts of calcium in order to take care of the salt. Why does it do that? Isn't that going to kill the plant? It might. But right now, the plant figures, I'm going to die anyway. When I've got that much salt and that much problem, I'm either going to empty calcium in order to compensate for the salt, and at that point, it either saves the plant or it dies anyway, which the plant figures it was going to happen. And so this is part of the problem for bitter pit. Okay, bitter pit in apples is because it's a calcium deficiency. When you empty the calcium is no longer there, and it's no longer getting into the apple, the fruiting structure. And so you've now got a calcium deficiency because it's trying to counteract a lot of the excessive salts. So this I just wanted to show again one more time just to make sure that you guys remember how important this chart is going to be, giving you an idea about where you need to be. I would like to thank you all for putting up with me. I'm pretty sure I made my 10 minutes. I would like to remind you all I still have some Mountain Dew up here, and that therefore I can answer some questions about electrical conductivity if Joe wants me to.
Absolutely. More Tom is like
Yes.
my goal in life.
Yes.
More Tom. More cowbell.
There we go. Okay.
Can you talk about green lightning and how it affects EC?
Yeah, I'm going to be talking about that tomorrow, but I'll talk about that now. Green lightning is a nitrogen source water. It's a treated water system. I'll be talking about that tomorrow morning. Because of that, it doesn't have the salts. So because it doesn't have the salts, you're able to get nitrogen into the plants without the salt. And so the effects have been quite good. And so I should probably tell you as a matter that I'm now consulting for Green Lightning. I'm also doing some consulting for Rainmaker too, but things are complicated. And so in order to help this process along, the Green Lightning has figured out a way through lightning. It's really just a lightning in order to get the nitrogen in there, and we don't have any of the salt side effects that are associated with the NPK fertilizers. You have a follow-up question? Yeah, I see what you're saying. That purple light is correct. That's a reaction to the nitrogen in the atmosphere. That's the reason why the light is purple. It's simply reacting to the nitrogen in the atmosphere. Good question. Yeah.
When you're taking soil EC readings, how important is soil moisture?
How important is soil moisture? It is important up to a point. Usually when you're taking a measurement, you want to know what it's doing at that moment, in particular with that amount of water that you have in it. Does the EC adjust with different water? It does. But the problem with that is that you're trying to standardize things in a laboratory. They try to get that perfect amount, whereas this becomes much more practical. So it will tell you what the conductivity at that point is. You may have low water, you may have high water, and that will adjust the EC a little bit because the conductivity will change slightly, but it gives you an idea at that moment in time, and that's part of the beauty of it. When you do the chemical analysis, where a little bit of water and a little bit of soil, which I assume is what you're referring to right now, if I'm reading your mind correctly, that is an artificial situation because that's not what's going on in your soil at that particular moment. So that's why we have these probes in order to just stick it into the soil to find out what is going on. It might change the next day or the next week, but it's very easy to do. It's a very inexpensive piece of equipment, and it will tell you a lot about your field. Yes, question?
I just wanted to know if you've had experience with paleo soils or the shale barrens as far as, people actually trying to grow crops on those areas and where they fit into this, organic versus inorganic connectivity.
I see. No, I do not have information to share on that, so it is a good question. There's just a lot of research out there. I haven't done it all, despite my claims that I have done it all, and trying to tell you that I know it all, because of course I don't. And you just brought up an excellent point that I'm not familiar enough to talk about. My apologies to that. Okay.
So how does the plant alleviate or neutralize the salt load in the soil? Actually, like where does the salt go so that it's no longer in the soil?
Where does the salt go? Usually it makes its way into the microbes. So one of the ways that is often compensated for it is to put a massive amount of sugar down in order to increase the microbial content. The microbes will take up the salt in exactly the amount that it needs, and the salt then becomes contained within the cells rather than being open in the soil where the conductivity will run willy-nilly at that point. Once it's inside the microbes, it's under control at that point. So that's one of the ways.
So the kochia that you showed, how does that do? Kochia plant?
Yeah, the kochia does it too. When kochia is, there are biochemical mechanisms and there are the physical mechanisms that I talked about. They are doing the same thing. They are able to survive, and therefore they are able to put nutrients into the soil, whereas if you did not have that, if you have a dead zone, there are no plants, and therefore the conductivity of that soil in the dead zone remains indefinitely, and it can go on for years. As soon as a plant is able to take root in order to start correcting the problem, it will. It is sometimes a slow process, But you must also understand that we've been trying to kill our soils, maybe not on purpose. We've been trying to do this very well for the past few decades. So we can't get out of it within one season. But the plants do it a little bit slower, and we can play games with them, such as, for example, I've told many about what to do. I said, give up what you can't do. So if you've got 1,000 acres and you've got, let's say, 20 acres of bad kochia, let it grow on those 20 acres. Allow it to work its magic. And then at the end of it, work it into the soil. Because that kochia, once it gets worked into the soil, will degrade. And every single biochemical reaction that is in that kochia was now going to get in the soil. It will now break down. So you will have the benefit when it was live, and now you're going to get the benefit when it dies and starts to break down on you. And therefore, there will be a huge improvement in just one season, but you just have to let it run, essentially fallow, in order for the weeds to do their job. I know I'm out of time right now. Thank you so much for paying attention to me. Hopefully, I'll see some of you tomorrow morning.
Excellent. Thanks, Tom. Appreciate it. That was awesome.
Thank you.
Like usual, and we get more of them tomorrow. So let's go ahead and take a quick 5.
We're so glad you enjoyed this installment from our in-person conference. We want this to reach as many people as possible, so we've decided to release this free to you bit by bit every month. But imagine how awesome it would be in person. The networking, questions, and discussions that result are equally as valuable. Join us next year in person for our 2026 conference. Your presence makes the experience. If you have any questions or needs, please reach out. Call, email, follow. We can help.